Hey there again. Welcome to our second video for the 3D coordinate system section. This is about worked problems, so I'll give you some examples here, and hopefully this will help you understand how to do homework problems. So let's start with problem number 1 here. It says identify and sketch the sets of points in R3 corresponding to the given equations. Now I've already written these ones out for you, and we'll work the rest of them as we go, but I just want to walk through these real quick. So in A, we're given the equation z equals 3. And what that's telling us is that no matter what point we look at in R3, we want that point to have z coordinate 3. X and Y are allowed to be whatever they want, as long as that last one is a 3. So if I were to come down here to this picture and I were to draw a coordinate in space, I could say, all right, maybe X is 1, Y is 2, and then Z is -1. Okay, well, that's a point in space, but it doesn't satisfy this equation because that last coordinate is not 3. So what I've done here is I've drawn a few points. So I have 1, 2, 3 right here. And then maybe we have -1, 0, 3, and then 2, negative, or no, 2, 0, 3. And this gives us a triangle in 3D space. And that triangle must be contained inside of a flat plane. And so here we go. We've got our plane consisting of all points with z coordinate 3. So if you have an equation that is just a variable equal to some number, you get you can think of that as a plane that is parallel to one of the coordinate planes, in this case, the xy. Maybe notice also that this is fixing z, and so the plane is parallel to the plane, or the coordinate plane consisting of the other two variables. Maybe a helpful pattern. All right, so now over here, if we look at the equation y equals 5, well, that looks very similar to the last equation we had, where we fixed z. So we might guess that this is also a plane. And that would be correct. It is a plane. Only now we have all of the points where the second coordinate is fixed. And so if we come over here and draw all these points, maybe our test point is 0, 5, 0. So our plane has to be parallel to the, we have y equals something. So x and z is the parallel coordinate plane, which means we have a plane looking like that. And it needs to contain this point. So it must be placed here. And then all of the other points inside of that plane are part of the solution set to this equation. Okay, last but not least, we have a set of 2 equations here. And so what we can do is we can draw the solution sets for each of these equations. So the set of points where y equals 5, we already know what that looks like here. And the set of points where z equals 3, we know what that looks like from part A. And we want all of the points, x, y, z, where y equals 5 and z equals 3. So that's going to be points that have to be on the vertical plane here and the horizontal plane. And the only ones that satisfy that are the ones here on this line. So these are points that look like x, can be whatever it wants, 5, 3. And that line, which should extend a little further actually. So these are infinite lines, and I just haven't drawn the planes all the way up to infinity. These lines are the solution sets of these types of equations, or systems of equations. All right. So that is problem 1. Problem 2 is similar, so we have some complicated equations. So it says describe and sketch the sets of points x, y, z satisfying these equations. So here, again, we have a system of equations. So let's go ahead and draw a coordinate system. And x, y, z, put that up a little bit. And let's see, okay, what do these equations mean? Well, x squared plus y squared plus equal 1 is in 2 dimensions the equation of a circle. Okay, so we might think, all right, for this one, all of the points that look like x, y, 0 and satisfy this equation must be in the solution set for that one. So what we can do is say, all right, if I look at just the xy plane, then I've got this circle right here of solutions. I can make that an actual ellipse looking thing. There we go. Okay, so we've got this circle of solutions in the xy plane. Except, wait a minute, this also works if I put a 1 there. And then what I have is that I can move this circle up 1 unit along the z-axis, and it still satisfies this equation right here. So what I really have is any set of points x, y, z, where z can be whatever it wants, and x and y have to be on a circle, which means I get to shift this circle right here up and down as far as I want. And well, what that actually looks like in 3D space is you just kind of drag and trace this circle up and down. And you get everyone's favorite shape. Okay, maybe not really your favorite shape. The cylinder. Come on. There we go. Okay, so this is a cylinder in 3D space. And that is just the set of solutions to that first equation. So notice it's only involving 2 variables, but I can still draw a 3D shape corresponding to it. Now we have this z equals 3. Remember, z equals 3 was this plane up here, so we can draw that. I'll just kind of scoot it in here. Oop, that's a terrible looking plane. And let's say this is at height 3. And you know what? Maybe we'll erase that one right there. Actually, I can make this easier for us. I'll just scoot that up and maybe move the plane around so that looks better. So there is our z equals 3 plane. And here's our x squared plus y squared equals 1 cylinder. And this circle that I just moved up is going to be our intersection. So the set of all points that satisfy both of these equations is this red circle right here. So it's a circle just shifted upward a little bit at z equals 3. Okay. So that's part A. Let's do part B here. Now I might have to draw this a little bit differently. So you know what? Yeah. Let's go ahead and use our first non-standard coordinate system. So normally I would put the x-axis here, y, and then z. What I'm going to do instead is I'm going to put the x over here, the do I want to do that? Yeah, the x over there, the y over here, and the z up here. So this is positive x, positive y, and positive z. And the reason for that is that now, well, if I look at the xy plane, it can sort of imagine this part, this flat bit rotated up, and then I'm just looking at the standard 2-dimensional plane that I normally look at. Well, I know that the graph of y equals x looks something like that in that plane. Shift this around a little bit. Right? It's at 45 degrees to the x and y axes. So we can say, all right, this is y equal x. Or really, because we're in 3D space, what I've just drawn is actually the set of points x, x, 0. So I still need that third coordinate there in order to specify this properly. But that 0 again could have changed to a 1. Or if I made it a 1, it would still satisfy y equals x, because the x and y coordinates are what they need to be. So again, we have this whole plane of solutions right here. And let's put that parallel. Move that in a little bit, maybe. Okay. All right, we'll leave it like that. So that is our entire plane, y equals x in R3. Now, if you can imagine something like R4, I can't, there should be even more solutions to this. There should be an entire three-dimensional space of solutions in R4 to the equation y equals x. And that's because if you have x, y, z, w, and z and w are free to vary, but x and y are fixed, they have to be x comma x, well, you get to choose x, z, and w. That's three different variables, so you have a three-dimensional space to work with of solutions. All right. Next up is problem 3 here. So it says, compute the distance between these 2 points P and Q. That period's very hard to see. All right, so let's go ahead and remember our distance formula. If you have it written down, go ahead and maybe write it down again. So we want the distance between P and Q. So if we just write down our formula directly, we have, let's see, we should have 2 minus 1, where I compare the x coordinates here. And then I square that difference. Now I have another term to add on. I look at -1 and -3. And because there are negatives here, be very careful. This is -1 minus -3. And then I square that. One thing I like to emphasize is be very, very careful with your parentheses. A lot of students aren't used to doing that, and it's a good habit to get into. Keeps you from making errors with negatives. Okay, so then we add our third term here. This is going to be 7 minus 5 squared. And we take the square root of that. So what do we get here? We get 1, 2 minus 1 is 1, and then square that is 1. And then -1 plus 3 is 2. Square that, you get 4. 7 minus 5 is again 2. Square that, and you get 4. So we have the square root of 9, which is 3. So the distance between these 2 points is 3. Another way that you could have done this if you wanted, just to make things a little bit cleaner, is to write out delta x, delta y, and delta z. This would have been 1, 2, and 2. And then you just square those directly in the formula. So you put them here, here, and here, respectively. All right, so that's a pretty quick one. Next problem says, find an equation satisfied only by the set of points on a sphere S with center 2, -3, 0, and radius 8. So this time we have an equation for a sphere, and we can just plug these directly in. So in that equation, we had an A, a B, and a C. Here's our A, B, and C. And this is our R. Maybe those A, And we have our equation for a sphere, S is the set of points x, y, z in R3. I'm being a little bit mathematical about this, but just bear with me. So all of the points x, y, z satisfying the equation x minus a is 2 squared plus y minus -3 squared plus z minus 0 squared equals 8 squared. Okay, so I can simplify this a little bit if I want. X minus 2 squared plus y plus 3 squared plus z squared equals 64. And that is the equation of our sphere S. This next one's a little bit more difficult. It says, show that this equation that they give us is in fact the equation of a sphere, and it wants us to identify the center and radius of that sphere. Running out of space here. I'm going to move things up real quick. And find the center or equation, center, and radius of the sphere. Standard form of the equation. So what we want to do here is try and rewrite this equation to look like this. Now, that looks pretty daunting at first, I'm sure. But what you want to do is pay very close attention to the format of the standard form. It has the x's in one term, the y's in the next term, and the z's in the other term. So if we were to just pay attention to the x's, we'd have x squared plus 4x. And I'm going to put a plus blank here, because we don't know what's going to go there just yet. But we have that plus, and now we're going to pay attention to the y's, y squared minus 6y plus 9. Oh, sorry, I gave that away actually. That was supposed to be plus blank sub y. It's going to be a 9. And then z squared plus 2z plus blank question mark z. And then that last thing that we have is the 6. I'm going to move that over to the other side. And then because I'm adding these question mark things to one side, in order to keep the equation the same, I have to also add them to the other side. So plus whatever these things end up being. And that is what we'll figure out next. So how do we figure this out? Well, there's a technique that you learned in algebra that you almost certainly have forgotten and maybe have never used since. It's called completing the square. So what we want to do is look for a number to put here so that this whole polynomial in just x can be factored as x plus something squared or x minus something squared. And I'll go through this one time. Then after that, it's going to be just you guys working it out on your own. But what we do here is we look at this middle number 4. We say, all right, 4 divided by 2 equals 2. And then I want to square that. Now, in this case, it turns out to be 4 again, but it won't always be that. So this is now our magic number. So that is question mark x. That's what gets added on. So let's see how this works. If I then put x squared plus 4x plus 4, well then this factors as x plus 2 squared. You can go ahead and multiply that out if you don't recognize that, but it does work. And so that's our goal. The next one here is going to be y squared minus 6y plus 9. And this is going to allow us to factor that term as y minus 3 squared. And the way I know it's going to be a minus is because that's a minus right there. And again, you can multiply out y minus 3 and y plus 3 if you want and see what the difference is. If you put minus, you'll get minus 6. If you put plus, you'll get plus 6. Okay. Next one, we have z squared plus 2z plus 1. A lot of these I just recognize because they're very common forms for polynomials. And this ends up being z plus 1 squared. And that's it. Now on the other side, we have to remember what we added on. So minus 6 plus 4 plus 9 plus 1. And what does that give us? Well, negative 6 and 4 and 1, that's negative 6 and 5, so we get negative 1. And then 9 minus 1 is 8, so we have 8 on the other side. Okay, but now remember that the standard form for the equation of a sphere has this side squared, so we need to write 8 as something squared. Well, that's pretty easy. How about the square root of 8 squared? Okay, and now once we have this written in standard form like this, we can immediately identify A, B, and C. Now you do have to remember, if you see a plus here, that means that coordinate is negative, and a minus means the coordinate is positive. And that's because, let's go back to our standard form equation here. The standard form has minuses in it. So if the coordinate's negative, then you end up seeing a plus when you actually write out the equation for a sphere. So our center C is going to be minus 2, 3, minus 1, and then our radius R is going to be the square root of 8, or 2 root 2. Okay. And let's do our last problem here. So we want to describe and sketch the region in R3 given by these inequalities. So now inequalities are a little bit different. We have an entire region to shade in here. So what we can do is pay attention to what these inequalities might look like if these were equalities, and then decide whether to shade in above or below those regions. So the z less than or equal to 0 we'll deal with in a minute. That's pretty straightforward. It's just a plane and then all of the points below that. But here is where we want to pay a little more attention. So x squared plus y squared plus z squared, that looks like the equation of a sphere centered at 0, 0, 0. Now, what they're telling us with the inequality here is that we are looking at all of the points on spheres of radius 1 up through spheres of radius 4 with that center at the origin. So if I were to zoom in here and draw an XYZ coordinate space, we could try drawing in our sphere. So here's our equator, and then I'm only going to draw the bottom of the sphere here, actually. That's not quite what I wanted that to do. Spheres are very difficult to draw. Let's see if I can make it work here. Yeah, come on. Close enough. Okay. So that is, maybe I can make this slightly bigger here. Make this a little bigger, and then we can start talking about it. There we go. That's more what I wanted. So there's our sphere. Let's say that's the one of radius 4. And then we're going to copy this and shrink it back down, put it inside here, and make that the sphere of radius, let's say 1. So we'll just go ahead and mark that. So here's -1, 1, 1. And then out here, we're going to have -4, 4, and 4. Let me fill that in a little bit. Okay, that looks slightly better. And now I only drew the bottom of the sphere because now I'm going to account for that second equation, z less equals 0. That means I'm looking at the coordinate plane in the x and y variables, and these guys are no, not these guys. This plane is then defining the edge of the region that I'm interested in. So now it says z less equals 0, which means I want all of the points underneath this space. So everything down z less equals 0, and everything on that plane, which means, that's the z equals 0 part. And then, well, I don't really want all of those points because they have to satisfy this inequality as well. So they have to have radius bigger than or equal to 1, and just realized I made a mistake. Those should be 2's. Less than or equal to 2. And it's 2 because that's a 4, and that is 2 squared to match the standard form of a sphere. Okay, so what we really want is, I don't care about all this, the z less than equals 0. What I do care about is everything inside of this sphere right here. That is outside of the tiny sphere. So everything inside the big guy and outside the tiny guy. Just like that. All right, and that is our region in R3. Okay, so that is all of our examples for this section. I may do another explanation video going over the distance formula and where it comes from. If I do, then you'll see it coming up right after this one.